Okay, in this video I'm going to introduce you to the concept of logarithms, and before I do I just kind of want to give you a little history lesson. Back in the, I believe it was the 14 or 1500s, there was a man by the name of John Napier, and he was a mathematician, and he came up with a system of making extremely long multiplication problems into addition problems, because adding large numbers is much easier than multiplying large numbers. And he spent about 20 years devising these tables. And I remember in high school I used these tables because we didn't have access to calculators. So they've been used for hundreds of years, and it's not been since the calculator came around that they've not really shown up in any of the textbooks. But anyway, let's just look at what a logarithm is. And first of all of these things listed is where you will see logarithms used. And you know, these words should be fairly familiar to you. And yeah, so we watched a few videos and looked at the different aspects of these, and it was pretty interesting. So here's our dilemma. Every function has an inverse, as we mentioned earlier in our studies. And we do that by switching out the x and the y. So if we just take our exponential function that we've been studying, and we come to the point where we know all of our inputs, which we know all of our x values, we can easily calculate our y value. But the question is, what if I want my answer to be 10? What exponent do I put on 2 to reach 10? And that caused a little bit of a dilemma. And so if we could find the inverse equation that could get us back to the exponent, then we would have it solved. Notice that the answer is going to fall between 3 and 4, because the number 10 falls between 8 and 16. All right. So again, this is the dilemma. How do we find the input that creates any output? And how do we find the exponent that creates any answer? So what if we just switched all of our x and y values? In other words, we found the inverse. And the 10 now became the input value. So we would have to find the inverse equation to this. And to find the inverse equation, we would switch out the x with the y. But the problem is we can't isolate this y. We have no knowledge of how to do that. Some of you suggested that take the square root. Well, that's a good thought, but that's only when the exponent is 2. And so the exponent being a y, that's not going to work. So Napier came along with this idea of logarithms. And it's simply just an exponent. It's the inverse function of an exponential. And much of what we're going to be doing in this lesson is just doing a conversion. But the most important thing you need to learn or know is that a logarithm can sound very intimidating, but it's just simply an exponent. And the domain and range of the exponential function, we know we can choose any x value to put into the function. So it's going to be all real numbers. The output values are going to be limited to just positive numbers, though. Okay, so when we take the logarithmic function, we'd simply switch out the x with the y. I'm going to show you how to graph the logarithmic function. So first we're going to start with y equals 2 to the x. Once again, those table of values. And we're going to plot these points. Okay, and the inverse function is found just simply by switching these x values with these y values. So I named these points right here because we're going to switch them out. We're going to plot these points right here, and we're going to see that they're just the inverse 3a, 8, 3, and so on and so forth, and we get the logarithmic graph, and that's what it looks like. It's also the reflection over the line y equals x. So in other words, I could fold along this line, and this would be the reflection graph. Or better yet, I could paint this graph, the exponential graph, folded along this line, and the imprint of that would be the inverse, and the inverse is called the logarithmic graph. Okay, so how do we write the inverse of y equals ab to the x? That's the question once again. So we could switch out those x's and y's, but once again, how do we isolate the y? It's not so easy. So we're going to use logarithms. And a conversion is necessary. But before converting, we need to remember the names of an exponential function. This is the base. This is the exponent. I think everybody should know that. So the conversion involves this little process, or understanding that a base is always a base when doing the conversion. So there's this little mnemonic device that you can use if you choose. It's called the 7 rule. It just makes this number 7 out of these arrows. And so if we're given b equals a to the c, and we want to convert this to a logarithm, we're going to start by writing out the word log. And the base is always the base. And we're going to switch the a with the c so that the logarithm is equal to the exponent. Remember, I said the logarithm is an exponent. So the 7 rule works like this. It looks like the number 7. So we know that a to the c power equals b. So again, this is just a little conversion into the inverse equation function. So let's take a look at a couple examples. This is a true statement. 64 is equal to 8 squared. So we're going to convert it into its equivalent logarithmic form. So we're going to start with the word log. And the base is always the base. So the base is 8. So I'm going to put the 8 there. And I'm going to set this equal to the exponent. So the 64 joins the logarithm. And we set it equal to 2. And there's the 7 rule. 8 squared equals 64. 125 equals 5 cubed. The first thing we're going to do is write the word log base 5, because the base here is 5. And we're going to put 125 equals 3. So you always set the logarithm equal to the exponent. And there's the 7 rule. 5 cubed equals 125. Okay, so the 7 rule is just an easy way of remembering the conversion. Just draw 7 as shown, and it will give the exponential form. So 2 cubed equals 8. 3 cubed equals 27. 4 squared equals 16. 5 to the 0 power equals 1. Okay, so hopefully that was helpful. And again, it's just converting. You're not really solving anything. You're just rewriting it into an equivalent form. So just like when you take the fraction 1/2 and write it in equivalent form like 3 over 6, they're the same numbers, but they look different. These are the same, but they just look different. One's in logarithmic form. Right. Well, one last thing. A common logarithm is known as a common logarithm because it has a base of 10. And your calculator will calculate base 10 only, because our number system is base 10. Whenever you did place value in elementary school, you had to name the ones, the tens, the hundreds, the thousands, the 10,000s. Those are all powers of 10. So our number system is base 10. So your calculator, the log key on your calculator, is calculating it in base 10. So here's the kicker. Whenever you don't see the base, it's understood to be 10. So you'll rarely see it written like this. You will most often see it written like this, which simply implies that the base is 10. And you can go ahead and use your calculator to calculate it. All right, I'm going to conclude this lesson right here, and I hope this was helpful.